First, I'll start with like an overview of what you can expect in this crash course. I know, like in the second half, like Zach, you saw it before, but I think for most of you guys, you haven't seen this before. Um, Basically, I'm going to be covering week one and about half of week two, the hydrostatics portion, before handing it over to Akshara, which is she's gonna deal with like continuity. By the way, this course, right? Unlike solids, it has statics and dynamics. So her portion is the fluid dynamics portion, whereas mine is mostly statics, right? Key points, like key topics I'm going to focus on is viscosity. I'm focusing on these because like in the workshop questions, they kind of emphasize these, right? So yeah, namely, I'm going to be focusing on viscosity and forces on a submerged body. For capillary rise, surface tension, and buoyancy, I'm not really going to touch on them. Those are topics that you're just going to have to refer to in your lectures because I won't have time. Because this course is really loaded with a bunch of small topics, especially in like the first few weeks, right? Yeah, and then we'll do a quizzes, which is like just test your knowledge or whatever, in the break. And then Akshara, again, she's going to touch on continuity, which is pretty much, if you remember back to dynamics in 1300, it's like kinematics of fluids, basically. And energy is basically like kinetics of fluids. And momentum we won't touch on in this course, but you will do it in this crash course, but you will do it in like week 5-ish, right? The second half of the course, we won't touch on at all, but hopefully this gives you like a good foundation to work off of, basically, right? Yeah, and she's also got a quizzes. So we've actually got 2 quizzes for you. In the feedback that we've gotten for these crash courses, people really like the quizzes because it's like a good way to gauge like how much you actually know, right, or whatever. So yeah, hopefully that'll be useful. All right, so moving on to the actual content. I like to start really broad when I teach. And like I've taught 1300 2 terms before, and so I like to think of everything in terms of 1300 basically, right? So this portion, like this course, it's built on the foundations of statics and dynamics, and those are built on Newton's laws. So Newton's first law is the law of statics. You can basically summarize it just from this simple expression of the sum of the forces is equal to 0. That's when things are either not moving or in static equilibrium. For example, if I'm not moving right now, I'm in static equilibrium, even though I'm on a planet which is traveling through a solar system, which is, it's like just not accelerating. But yeah, anyway. And then when the sum of the forces is equal to ma, that's in the case where things are moving. In other words, it's accelerating. So yeah, that'll be useful for when you have like pipe flow through water, for example, right? Whereas the first case is better for when a body of water is still, and something you'll learn about called hydrostatic pressure. The pressure due to water's inherent properties is building on to like a gate, whatever, just causing it to have like a bending moment or whatever, for example. In terms of speaking very generally, let's talk about material properties for a second. So, an object or a thing basically can be broken up into whether it's in solid or fluid form. So if you remember back into material science or even like chemistry or whatever, back in, I don't know, year 7, there's like solid objects, there's liquids, there's gases, right? Fluids basically encapsulates the liquids and gases portion, right? And there's like these brief definitions which I've included. So solids are things with a fixed shape and a fixed volume, whereas liquids have no fixed shape, but they have a set volume, basically, right? So you're thinking about like, if a liquid's moved from container to container, it can have the same volume, but it will just be in a different shape. It will mold to the shape of the container, right? And gases don't have a fixed shape or a volume, and this is due to them having a lot of space between its particles, and it can be compressed, for example. Oh yeah, I forgot Sue was coming. Hi Sue. Yeah, but the pattern kind of goes like this. These are fixed. Oh. So if you want to look at it visually, it's like this. My notes, by the way, they're in the chat if you scroll up. So if I scroll too quickly or whatever, and you need to look at the notes again, you can look at it through that. Or you can just download my notes and then draw over it if that saves you time. Are we all good so far? Yeah. Okay. Let's talk about some fluid properties. So the very first thing they dive into for this course is just familiarizing you with what fluids kind of are. And there's a lot of common of these like properties that you're gonna have to be familiar with to do the calcs. The first one's density. This one's probably the most intuitive. This is basically your mass. It's denoted by this Greek letter rho, and it's mass divided by your volume. So here I've drawn volume in a weird way. You've probably never seen this symbol before, but sometimes they just write V for volume. Sometimes they write this V with a dashed line through it. Yeah, that's his volume. And in terms of units, this will be in kilograms per meter cubed, basically, right? So density is a three-dimensional property, pretty much, right? Unit weight, all you do to get unit weight is you multiply density by 9.81, which is your gravity constant. You know, unless you're talking about like aerospace or like, you're on the moon or something, then it'll be different. But like, obviously, every scenario they give you is just going to be this one, right? And so basically your mass becomes a weight force instead, right? So this is your m times g, if you remember back from physics, right? And so since it's a force, it's going to be in newtons per meter cubed, if you're talking about SI units, pretty much, right? There's common data for water, because I guess like in fluid mechanics, you're going to be working with water a lot. There will be other cases, you might be working with mercury or a couple of other types of fluids, but basically since you're going to be working with water a lot, and the properties of water is very, like, they're not hard to remember. You're expected to kind of just know these off by heart. Water is 100 kilograms per meter cubed. It's also 1 gram per milliliter. So remember there's anyway, you look up the conversion from meters cubed to liters, basically, right? I'm not going to write it because I'm going to get it wrong. But yeah, because you'll be converting from liters to meters cubed a lot. This one is your unit weight of water. So again, same thing, but you just multiply it by 9.81. Makes sense so far? Next thing to talk about is specific gravity. So your specific gravity is basically the ratio of whatever fluid you're talking about relative to water, right? So, for example, sand. This is not something you see in this course, but this is something you see a lot in soil mechanics in term 3 for a lot of you. Sand is 2.65 times heavier than water, basically, right? Concrete is 2.4 times heavier than water. And reinforced concrete, which is basically just concrete with steel inside of it to bolster its like mechanical properties, is about 2.5. 2.5 heavier than water, basically, right? Yep. Any questions so far? Okay. So chuck your hand up if you've done material science. Yep. Okay. It's all good if you haven't done material science, because I'm going to be going through these briefly. This is kind of stuff that it's not really assumed knowledge, but it's stuff they skip over, and it helps to know the background in material science. So it helps if you've done the course, but yeah, if you haven't, it's fine. So the first thing to talk about, let me just pull up my notes quickly. Yeah, so the first thing to talk about is our elastic modulus, which is sometimes called Young's modulus. So even if you haven't done material science, you might have heard this from either engineering studies in high school or even physics. They might have brought up Young's modulus before. So this is a measure of stiffness, right? Yeah, we'll just leave it at that for the moment. It'll make more sense when I bring up the other stuff. Sorry. The shear modulus is a related property, but yeah, I'll come back to that. Just explain later. Yeah, basically, for solids, what I'm trying to point out here is that solid materials will follow these kind of material properties, whereas fluids, they're going to follow a different one, essentially. So let me explain elastic modulus for a solid first, because it's going to help with explaining bulk modulus in a second. So your elastic modulus is the ratio between your stress and strain. That's the basic definition. But firstly, like, if you've never heard of stress and strain before, stress is force divided by area, and strain is your deformation. It's also called delta L, which is change in length, right? Over its original length, essentially, right? In terms of units, we have, you can find this in pascals, kilopascals, megapascals, and this one's unitless because you have whatever, like meters divided by meters, so it becomes unitless, right, with your strain. Pascals is newtons divided by meters squared, so that's where, yeah, it's like your force divided by area. So yeah, when you have like this tensile piece in a lab and you're testing it, it's being pulled apart. Essentially, that force there is a tensile force, right? And your cross-sectional area is this one, right? So the strain, so you can think of stress like a force, but it's distributed over an area, right? You'll get very familiar with this in the second week of solid mechanics if you're doing that course. But if you have the same force and you have a larger area, for example, so if your cross-sectional area was actually that big, the stress on it would actually be less, right? Because it's divided over a greater area. In terms of strain, so that's your original length for our test specimen, and however much it deforms would be your delta L, your deformation, right? So yeah, strain is just a measure of deformation, whereas stress is a measure of forces relative to your cross-sectional area. No, they skip over this in fluids because they talk about what I'm about to talk about next. But it makes more sense to think about it in solids because this is the simple case, basically, right? So, bulk modulus, right? Essentially, your bulk modulus, it's going to look very familiar because it's also going to be in pascals, kilopascals, megapascals. But essentially, the difference is this applies for fluids. This is a fluid property, right? So pressure is basically your fluid version of stress. Think of it like that. It's also known as the bulk stress, right? Your bulk modulus is sometimes denoted by K. I think it's also sometimes denoted by capital B, but it's equivalent to your elastic modulus, but for fluids, right? And your strain is going to be three-dimensional now, right? So here's a diagram for this is like an elementary particle of a fluid material, right? Like a fluid, and that's how everything would slot in. So it's about like, instead of about tension, it's about compression. Basically, you're thinking about it like you're being compressed from all sides to have a reduction in volume. That's actually where this minus sign comes in, because since your bulk modulus is a measure of compressibility, yeah, the more the volume reduces, the more compressible it is, right? Yeah. Yeah. Does everything make sense, hopefully, so far? Okay, cool. The next thing is the shear modulus. So now we're actually jumping back. So I've kind of jumped back and forth. So I've talked about solids, talked about fluids. Now I'm talking about solids again quickly, but in relation to shear modulus, right? So when we think about our solid before, and as a tensile test piece, the tensile force, what kind of force is that in terms of, is it an axial force? Is it a tangential force? You know what I mean? What kind of force is tension, I guess? It's axial, right? And so the difference is, for the type of forces we're dealing with, for shear modulus, they're parallel to your surface, right? The tangential, there's all sorts of words for it. But yeah, that's the kind of forces we're looking at. And yeah, this becomes your shear area here. Think of it like this, right? I've got a cardboard box full of, like, I don't know, Sevsock merch or something right here in front of me. I'm pushing it like that, right? And the shear area is actually like here in that case, right? It's scraping against the ground, right? And the part that's in friction in that particular scenario would be our shear area, right? Yeah, and then in terms of shear strain, it's denoted by gamma as well. Don't be confused. This isn't the same gamma as unit weight, right? But it's about your deflection in this direction divided by the original length in the other direction, like that. Okay. Anyway, so these are all solid properties, basically, right? Viscosity is essentially your shear modulus for fluids, right? And I'm going to write this down quickly. Oh, what the fuck? You want to think about a fluid as like layers which stick together as your shear stress is being applied to it, right? Here's your shear area, basically. And yeah, so here we've broken up this fluid into kind of like discrete layers, essentially, and they're trying to like stick together, right? And yeah. So we moved on to velocity distribution. Have they talked about this in the lecture? Like, did they mention this? Yeah. I'm getting a nod over here and a head shake over here. Do you have two lectures this week? It might be starting from the second lecture. Oh, okay. Maybe they didn't talk about it this lecture because they're talking about like assessments and stuff first. It should come up very shortly, but this is like the first like kind of loaded topic. So imagine you have this scenario, right? Aim the camera over here. So basically, these are two plates, so you can think of like 2D, whatever. One's moving, so it's being dragged by like a force, like that, and this one's completely still, right? Here I've overlaid two kind of distributions. This one is your velocity distribution, right, which is denoted by u as a function of y being the status scale, right? And here is your shear stress, right, distribution. And this is your base case. This is your simple case, where we have a linear shear stress distribution. Oh, sorry, a linear velocity profile, I guess. So that's linear, right? Let me just write out a couple things. So what I have there in purple is how fast the fluid is moving as a function of y, right? Which makes sense because at the very bottom here, the fluid doesn't want to move, like that fluid particle closest to the edge, it doesn't want to move because it's trying to stick onto the thing that's not moving, right? Which is your fixed plate, right? For a fluid particle at the very top edge, that's moving at the top speed. It's moving at the same speed as your moving plate because it's sticking to the plate that's moving, right? And then you have like this profile that's linearly distributed in this case that follows that, right? Let's talk about the shear stress in a bit more detail here. So it's denoted by this Greek letter tau. And very similarly to axial stress, it will be your force divided by your area. Difference is here, we're talking about different forces and different areas compared to our axial case. We're talking about our shear area for A, right? And we're talking about our shear force for F, right? Which is the parallel to your plane one, right? There's another formula for this, which is very important. All right, so this is mu, right? Okay, I'll explain this. So mu stands for dynamic viscosity, right? So this is kind of a new concept. Its units are pascals multiplied by seconds, right? And it's basically a material property. It measures the resistance to flow, right? You can see in the corner here, this is a predictable number for water, right? That's mu of water at 20 degrees. So you can see that it's like temperature dependent as well. Our normal case is that it's at 20 degrees basically. So that's the number you're going to be using. What I've drawn here, capital U divided by capital Y, this is your velocity gradient, right? That's your gradient, so the slope there, right? So U, max U, is denoted by capital U, so that's this number here, and it's divided by your total depth. And you can only use this formula if it's linear, right? It's same as when you were graphing straight lines in year 8, right? Remember this, y equals mx plus b. The slope m is rise over run, right? That's the same thing. But you're only allowed to use that as long as you're not dealing with like a parabola or something, right? Yeah, straight line. Okay. Another thing to note is your kinematic viscosity, which is basically your dynamic viscosity divided by the density of your fluid that you're talking about, right? So for water, it's also a predictable number, right? Because remember, water was 1,000 kilograms per meter cubed, right? So it's just, yeah, anyway. The units is meters squared per second, right? Yeah, anyway, sorry, I'm going through this very in depth, but a lot of the questions will be on this topic. That's why I'm like explaining it quite deeply, right? But I will try to speed up for the following bit. Does anyone have questions about this? Yeah. So mu or u? So lowercase u or uppercase u? Both?
Uppercase u is max of
Yeah.
But what is
U is velocity.
Oh.
So the speed at which the fluid is moving.
Oh, okay.
That's it. Wait, just quickly, I'm just going to conclude that thought. So U bracket Y is the velocity as a function of your depth in the water, right? In this case, we're going this way, right? Oh, sorry, I wrote it here.
Oh, it's going upwards.
Yeah, and then your total depth is capital Y, and your max speed is capital U, right?
But because it's linear.
Yeah.
Okay, sure.
Yeah. This term here is your velocity gradient, because it's just the slope of your velocity, right?
And what's tau?
So tau is your shear stress, and yeah, it's just think of it like force divided by area, but it's also got this additional formula. Most of the time you'll find yourself having to, in the questions, equate these two parts together and then sub in the missing algebraic, you know what I mean, right? Yeah.
Is that like the official formula?
Yeah. Official formula. Yeah. The only thing that changes ever for this is that's not necessarily always like constant, right? Because the gradient's not always constant. I'll show you an example where it's not constant, right? So here it's not constant, right? Here you've got a moving gradient, basically, right? So therefore we have to use your calculus du dy. That's a it's a function. It'll be a function of y, basically, right? Yeah, makes sense. Okay. I'm just showing you a few different scenarios here. I want to ask, in this case, right, we have one moving plate, which is the middle one, and we have two fixed plates, right? And say we have a linear velocity distribution. What would the shear area be? You don't have to give me a number, but like how would you find it? I'll draw out this in like a perspective view. So that's a moving plate, right? And it's being pulled like that way. Here's your fixed plates on the top and bottom, right? Be underneath, but it'll also be on top, wouldn't it? It's not because of the fixed plates. Well, kind of is, but like basically, there's fluids on both both above and below it, right? So your shear area is actually going to be shearing here and here on the plate, right? So actually, it's if this is B, so B is your width going into the page. So you can't see it in this elevation view here, but I've listed B on the side here. B multiplied by L, right? That's that rectangle there, right? It'd be 2 times that, because it's the top and the bottom part is being sheared, right? Yeah, so shear is that. Let's look at this one, right? This one's fried. So you have like a fixed outer cylinder, and then you have this moving inner cylinder that's being dropped through it, and it's moving at a constant velocity, right? So what would your shear area be for this? Let's have a think about this. So shear is like parallel forces, remember? Parallel to the movement. Of the object shearing against the water, yeah. And the water, yeah. Okay. So this whole thing's moving down, yeah, due to gravity. Like W is the weight force, right? Basically, the shear area looks like this. It's on the outside of the inner cylinder, right? So that's what? Pi d h, right? H being your height. So this is literally like geometry from like year 10 or 9 or whatever, right? Right. And your velocity profile in this question, you have to enhance to see this shit. That's how it's moving, right? Because the fixed plate in the drawing that I've done is on the left, and the moving plate, which isn't a plate, it's a cylinder, is on the right, yeah? Makes sense? Here's another case. Basically, we have a fixed outer cylinder and then a moving inner cylinder, except instead we have, it's twisting, basically, right? You have torsion essentially acting on it. And so what would the shear area look like, you reckon? So again, this is parallel forces you're thinking about. It's gonna look like this, right? So essentially the same part of the cylinder is shearing. It's just the forces is being applied. Yeah. Like kind of this way. Right. Rather than that way. Right. Any questions?
Is this the only four scenarios we're going to get?
Sorry?
Is this the only scenarios we're going to get?
Only scenario.
The only possible scenarios we're going to get?
This is the most complicated one I've seen.
Oh,
So it doesn't get any harder than this, basically. Yeah. Yeah, so I didn't cover surface tension, capillary, and vapor pressure, but these are still part of your week one like fluid properties, basically, but they're lesser topics, basically. If you want to have a good read of someone's notes, I've sent through Barney's notes. They're incredibly good. They have all the formulas you need in case they do throw you a question. But in the workshop questions, I didn't see anything to do with these topics. But like, it might just randomly be a multi-choice or something in like a weekly or in like a midterm or so it's good to do that as like a low priority study thing. I haven't talked about hydrostatics yet, so I'm going a bit slow. All right, hydrostatics. So before I was just talking about general fluid material properties, essentially, right? Now we're talking about hydrostatics. So these are for bodies of water that don't move, right? The first thing to realize is that pressure varies with depth, right? Linearly, essentially, right? This is kind of a gruesome example, but like, do you remember like the submarine full of like rich people that went? What was it called again? What? Ocean Gate. Yeah. So Ocean Gate went really deep into the ocean, and it imploded essentially, right? Due to hydrostatic pressure, essentially, and everyone inside got like compressed essentially. So that's what bulk modulus can do. It's about compression forces essentially, and yeah, as gruesome as that is, it's good to think of that scenario when you think about what water does in terms of pressure, right? Hydrostatic pressure. Yeah, so we're just going to dive into it. So we have 2 points that are randomly drawn here. And do you see how I've drawn them like laterally, like they're just a bit off center, right? It's because the only thing pressure varies with is depth, not like this horizontal position, okay? And so we can still do calcs on these 2 points, even though they're like that way, far apart, right? Here's the general formula. So the pressure in spot 2 is the pressure in spot 1 plus, this is your unit weight, right? Multiplied by height, right? Alternatively, you can call this rho g if you're doing your calcs like that. And we also know that atmospheric pressure, so here you've never seen this before, but it's the first time you're going to see it. It's a downwards triangle of 2 lines. This means where your air is touching your water, basically. You're going to see it a lot in your degree. And so atmospheric pressure is going to be like all of this is going to be at atmospheric pressure pretty much, right? And so if you wanted to find the pressure at point 2, given that you've had the one at point 1, then you just add it like that. Otherwise, if you start, actually, you know what, I'm kind of overcooking this explanation. We'll leave it at that, right? But just keep in mind there's 2 types of pressure. There's absolute pressure and relative pressure, okay? And so absolute pressure would include your atmospheric pressure as your baseline. But relative pressure is only the pressure added on top of your atmospheric pressure, right? So yeah, you'll see that come up in questions. Oh, do we have questions so far? Yeah, I'm gonna go a bit quicker. Manometers, right, is just a measuring device for measuring like your pressure in a pipe system. And here's a cross section of a pipe. So there's a pipe flowing, like going in and out of this page like that, right? Then you have your manometer connected to it. The base case is that on one end you have your pipe and the other end you have it's open to the atmosphere, right? And then you're given this fluid height, and then you calculate the pressure in the middle of the pipe, right? Here we have a U-tube manometer, and you're given atmospheric, it's touching the atmosphere here. You have to add on the pressure due to mercury, and you subtract off the pressure of water, right? So it's going to come up with some pretty funky equations, but I'll just jump. Yeah, here's another case. These are your differential manometers, which has two cross sections that are measuring off of each other, so it's not connected directly to the open air, right? Here's an example of an equation. So the pressure at B is equal to the pressure at A minus off this pressure. It's minus because your depth is increasing, as in like it's going upwards, right? And since it's going upwards, you're relieving pressure, right? And you're relieving pressure again, and then finally you're adding pressure for this third type of fluid, right? Does that make sense? Okay. Sorry, this makes more sense when you do the questions than if I'm just like loosely explaining it to you. Here's my last topic that I'm going to talk about, and this one helps if you've done 1300. Can you chuck your hand up if you've done 1300? I actually already knew the answer to that question, sorry, Anushka. But like, yeah. But yeah, basically, this is the only part of this course where statics from 1300s like comes in. So I'll show you the default case. Here you have a floodgate, right? The floodgate is like a solid material, right? And you have this pressure distribution due to water, right? And it linearly increases, like I've been saying, right? So you have this like triangular distribution. Here I've drawn some seaweed, but this is just to show you that it's like elevation view, right? So side on, basically, right? Yeah, these are the general formulas, but let me show you how everything plays into account. So we're looking at this floodgate, right? And we're looking at, so H is height, the height of your floodgate. Here is rho GH, which is your pressure at this depth, right? So we're measuring like the biggest part of that pressure distribution using that. And the way that I've gotten the force is literally the area of that triangle that I just drew. Literally the area of this red triangle. What I do is half times your base of your triangle times your height of the triangle, right? That's it. However, this is newtons per meter, okay? Because this is per meter run into the page. Got it? Because your actual force, if you're given a width b, right? So this is actually the b dimension going into the page. So that's the one we can't see in that diagram there. Yeah, that's our pressure distribution prism. Looks like that. Rho GH, that's H there, right? That's our seaweed. Right. And then, so the actual force is the volume of this pressure distribution prism, okay? This 3D shape. That's how you calculate the force, okay? From 1300, you might remember your equivalent point loads, right? Which is just reducing this distributed load into one point load. It works the exact same as it does for loads in 1300. So for a triangularly distributed load, it's 2/3 from the small side, 1/3 from the big side, and the force is just what we calculated from before, right? Yeah. That'll make sense later. I'll elaborate on that. So here's our first scenario. And basically, before, our gate was touching the top, right? So it's a triangularly distributed load. However, now our gate is some amount of depth into the water before it even starts. So the pressure on the gate is actually going to be trapezoidal, okay? By the way, this is just a stupid thing, but you're gonna see this come up a lot. So this is all this gate, except they don't explain what this is. This is the cross section of the gate, right? So it's like if you're looking at this gate like this way, it's your eye. That's what that is. Yeah, it's not like some random gate that's like just there. It's the same gate. It's just you're looking at it from a different angle. They never explain it to you, but that's what it is. Okay. And then here's the pressure distribution acting on, again, this gate. So it's actually like that, right? Anyway, so we have a P min and a P max this time. So we're just measuring the dimensions of our trapezoid, essentially, right? And then we have that formula. And here's our pressure distribution prism, right? And in order to get the force, you get the volume of this shape, and then you get the force, right? Point of application, YP, that's this depth here. My notes. Yeah. So basically, YP is what I was talking about earlier. So this would be YP. It's the point which you're applying your force on your gate, right? It's where the concentrated loads would be. For a trapezoid, it's a little bit harder to find, right? Because YP is like this number. YP is like kind of a bit harder to find when it's a trapezoid, essentially, right? Because it's not necessarily 2/3 from the small side. YC, this is where your solid mechanics will come into play, because YC is your centroid in the Y direction, right? So that's a geometric property of that gate, because again, this gate is a solid, it's not a fluid, right? So we have to apply our solid mechanics knowledge to this. Yeah, this is what I mentioned earlier. So for a triangle, YP is just 2/3 of the height, right? So two-thirds from the small side. Okay, basically I'm just scaring you because I think there's a better way to do it than integrating. You can apply this formula if you like. But also this is your parallel axis theorem. Sorry, that's your moment of inertia, geometric property from solids. This is your parallel axis theorem. Sorry, Nishka, I'm probably speaking like a fucking different language to you right now, right? We'll run over this later, but I'm just conscious of time, so I'm gonna speed through this a bit. This is good. I'll send you the part that's relevant in my solids crash course, because this will make more sense of solids, right? But essentially, this is useful when you have gates which aren't rectangles, right? Rectangle is like the default case for gates, but here's a triangle that they could run over in the lecture. You might have a circular gate. I've run a circular gate in one of the questions before. Yeah, that's why it gets cooked, basically, right? But here's my trick for trapezoids, essentially, right? Because the easiest way to do it is actually breaking it up into a rectangle and then a triangle, because that's all a trapezoid is, essentially, right? And when you do that, you can find the forces very easily, as well as the point of application. Yeah. So because this point of application is going to be hard to find for a trapezoid, you just break it up and then you'll find it based on, yeah, anyway. Yeah, that's the end of my section. These are some geometric properties, your moment of inertia from solids, but yeah, okay. Does anyone have questions? All right, do a quick smoker, then we'll do a quiz, then we'll hand it over to Akshara. How about that? All right, so yeah, 36%, let's go. Yeah, last time was 25%. Okay, so bulk moduli, right? Yeah, it's a measure of compressibility, but basically a higher bulk moduli means that it's less compressible. So a solid has a higher bulk modulus than a water, which has less than air, right? So do you remember the negative? The negative makes it the other way around. So like steel has a really it's basically just negligible. That's why it technically exists, but since like the number is so irrelevant for compressibility of a solid, they don't really care, right? Okay, so shear area of this scenario. Thanks, Henry. See you, man. Bye. Yeah, this is what we talked about earlier. It's your cylinder's circumference multiplied by its height, right? The inner cylinder, right, not the outer one. Because the outer one's a fixed one, right, from what we talked about before. So this is a pretty hard question, to be honest. So the most common wrong answer was basically this is a closed container, and so we don't have atmospheric temperature necessarily inside there, even though that is air technically. So the question is also possible to answer despite not knowing maybe the difference between these two heights, the top surface of the water and where the mercury ends, because air's density is so negligible, it doesn't really change pressure in air as a medium, basically, right? And then lastly, the height between the top of the water and the inside end of the tube doesn't matter for the reason I just said. Yeah, so this distance here doesn't actually matter because it's so negligible, right? Yeah, so this one's, I know it's a hard question, like conceptually, but I wanted to include it because I didn't really have time to talk about it. So I just thought I might see who would have a good crack at this. Basically, right, I'm going to overlap this. The pressure distribution at these 2 points, because they're at the same height, right? Point A and point B are at the same depth. And so they have the same pressure. So we actually have a linear pressure distribution. And the pressure is acting at the gate, which is that point of focus. Kind of put like down arrows for acting at that. Whereas between B and C, it varies of height. And it's not going to be a triangle because we know that it already is not on the top surface. So this is the case that we talked about before. This part of our gate. This is kind of new. This uniformly distributed part only happens when we have a completely horizontal. Okay, there we go. Right. This way?
Yes.
Good. Yeah, just when you're ready.
Okay.
Alright, try that.
Ready? Oh, thank you. So we're going to learn about oh my god, this thing. It's a bit of a Wait. Should I mute? Okay, but they'll hear it in your laptop, right? Okay.
It's fine.
Okay. So continuity. This is the second week of the fluids course. So I'm going to be delving into the different types of continuity questions that you guys could get. They're all largely based around the same principle though. So as long as you get the principle of like conservation of volume and mass, you should be able to solve any continuity problem. And then in the second part of my section, I'll be delving a little bit into like the energy equation and Bernoulli's equation and how that relates to continuity. Okay, so starting off with the first concept, flux is basically another word for flow. So in your problems, in your continuity problems, you will be asked about 3 types of fluxes, 2 of which I'm going to go through in quite a bit of detail. So the first one is volume flux, as you can see. The units for those are meters cubed per second, and the symbol is Q. Before I go on, I should probably mention that, or at least I found with fluids that the units caught me out in a lot of questions. So I would be really careful when like converting between the units, let's say in the question, and then the units they ask for in the answer. Okay, yeah. The second part is mass flux, which is just very similar, but it's in a weight per time form, so kilograms per second. And the symbol for that is M with like a dot above it. I don't know if you can see that. And then the equation is P times, or like density times Q, which you found up here. So for example, a question that you might get is to find the mass flux of like a control volume, which I'll explain what that is in a second. But if you have to find the mass flux, then you usually have to find Q, which is volume. And then the third one is momentum flux, which you guys will learn a bit more about in week 5. But yeah, it's just a similar concept as well. Okay, so I think the easiest way to kind of explain what flux is to go through like a very simple example. So this one here is just finding the volume flux Q through a very simple system. So a 0.5 meter diameter pipe, and you can see they've given you the average velocity over the cross section. So you'll notice that in the volume flux formula, you've got an A and a U. U represents the average velocity, which they've given you in the question, and A will always represent the cross-sectional area through which the liquid or the fluid is flowing. So in this case, with a pipe with a diameter of 0.5 meters, we have to find the area of that circle before we find Q. So I've just done the working out for you here. I've inserted the area of a circle formula in there for you to see, and then I've multiplied it by 2, which is the average velocity that they gave you in the question. Does everyone understand that example there? Great. Okay. Another way that they could make the question more complicated is, like I said, including mass flux, which would get you to question, I guess, the density as well as the volume flux. So here they've given us the same question, but there's 2 different types of formulas. One is freshwater and one is seawater, both of which have different densities. So it's almost the same. You just take the Q that you found in part A, so the 0.393, and you multiply it by each density to get your mass flux. Okay, so just a bit of terminology before we move on. So often in this course you'll get a few terms thrown around here and there, 2 of which are quite important. So incompressible and compressible flow. Fluids in general can be liquid or air, and then depending on which one it is, that will determine whether it's incompressible or compressible. So incompressible fluids, the fluid that you'll be working with pretty much in this course all throughout, have constant densities. So that's when the water, that's like usually water of any kind, and then air when the velocity is less than 100 meters per second. Compressible fluids are where the density actually varies in the fluid, but you won't really be looking at that in this course. Does everyone understand the difference? Okay, so the third section of this unit is solving fluid flow problems. So you'll remember I mentioned that the principle behind all of these problems is pretty much the same. There are three methods you can use to go about solving fluid flow problems, two of which I'm going to go through with you today. The first is the mass/continuity equation. That's the simplest equation that you can apply to any continuity problem. The second is the energy equation, which I'm going to go in depth with. Well, I'm going to go into depth like in the next section. And then the third part is the momentum equation, which you guys will learn about in week 5 or week 4. So before we get into any actual problems, I just wanted to run through quickly what a control volume is. So understanding what a control volume is basically allows you to visualize any pipe flow or any fluid flow problem. So when you're given a problem, you won't always be given the diagram, which means you often have to visualize it yourself, and you'll have to draw the diagram yourself. And you can't really do that without defining your own control volume. That means determining where your fluid is flowing, the direction it's flowing in, the shape of the water storage section, which is, let's say if you've got like a pipe expansion, or if you have water flowing out of a tank, then that like section or storage section will be like a cylinder, let's say. So in any continuity problem, the number of equations is equal to the number of unknowns. So very similar to when you were probably like in high school doing simultaneous equations, it's the same thing. And then the second part is to select a control volume, which I will go into the different types in a second. A couple of things to consider when defining your control volume is that the control volume can be finite or infinite, but it has to have boundaries, which is called the controlled surface. The boundaries can either be fixed or they can be deformable. So that would be like a free surface, for example. And then the control volumes, they can only contain fluid, so liquid or air. All right. Over here, we kind of have some examples of control volumes. The first three are kind of important with the diagrams to the right. So they kind of show that with each continuity problem, depending on what your control volume is, that will tell you whether you're working in like a single dimension or multiple dimensions. So as you can see in the first problem there with the pipe junction, you're only considering the horizontal direction, or the flow in the horizontal direction, velocity in the horizontal direction, right? But then once you get down to like the tank or reservoir, there's obviously a change in the depth as well. So you're considering the Z direction as well as the Y direction, because you've got quite a large storage area that considers both the X and Y direction. Other terms that you might hear when solving continuity problems is a pipe expansion. So I'll go through a pipe expansion example with you in a second. Things like moving trolleys, weirs, plates, pipe junctions, I'm going to go through that with you as well. They're all types of control volumes that will help you visualize a continuity problem. Okay, so I'm going to run through a couple of examples now, so continuity examples. The first one I'm going to go through is using the continuity equation. So remember, that's like our first method out of 3 methods to solve pipe flow or fluid flow problems. And we're going to solve or use the continuity equation to solve an example in a finite-sized control volume. So problem type 1 is a fluid in a control volume that does not change in volume. So this is where the input is equal to the output in mass and volume. So this is the derivation here, but it basically is derived to become this equation here. So the sum of the volume flux inside the control volume is equal to the volume flux out that leaves the control volume. If you're going to note down anything, I would say make sure you note down these, just because they're the assumptions that you make when you're using this equation. So we're assuming that we're in a closed system, like pipes, for example. We're in a steady state flow, which could be a river. We're using a constant density, which I mentioned when we were defining our control volume. That's very important. And it's a steady, we have a steady fluid boundary. Okay, so this is the example here. So all they're asking you to do in this question is to determine the velocity at 0.1 over here and 0.2 over there. So as you can see, at 0.1 we've got quite a small diameter, 0.4, and then the diameter doubles at 0.2. So they've given us both the diameters, they've given us the volume flux at 0.1, and they're asking us to find the velocity at 0.2. So just before we get into the solution, does anyone have any idea of how we might, get more information from what they've told us already? About 0.2, I mean, because they've only given us the diameter in 0.2. Yeah? No, actually. So these questions, the continuity equations, they don't include pressure because we're only considering the movement of the fluid. Yeah. Sorry, what did you say? Almost. So remember, this is continuity, basically. So the whole idea is that the volume flux inside the pipe, or that's going into the pipe, is equal to the volume flux going out of the pipe, which means that even if they haven't given you the Q at 0.1, it doesn't matter because the Q at 0.2 is going to be exactly the same, right? So as you can see in this example here, the first step is to define your control volume, which is a pipe expansion. And step 2 is to apply the continuity equation. So we know that Q is equal to the velocity times the area, which means we can solve them both into, we can solve them both into this equation here. Regardless of how quickly the fluid is flowing through the pipe, both Q's are going to equal 0.2, which is why we can put the 0.2 at the middle of this equation here. Can you guys see that? Okay, so here you sub in your 0.1 values, and here you sub in your 0.2 values. So at 0.1, your diameter is 0.4 squared. We haven't been given the velocity at 0.1, but we have been given the velocity at, oh no, I lied. Sorry, my bad. You haven't been given the velocity at all. So you just use the Q and you separately solve each equation to find the velocities at 0.1 and 2. Does that kind of make sense there?
Sorry,
yes?
With that equation, last time we ran the fluids workshop, people were a bit confused. There's not one here.
Yeah.
It's equal signs, right? So it's 0.2 is equal to all this shit U1 is equal to all this shit U2. So you solve that part as U1, and that one is equal to that one for U2.
Yeah.
Right? I think people thought that was a plus before.
No, I just made that mistake. I made that mistake explaining it to them. But you solve each equation separately to find the velocity at 0.1, and then you use the same value to solve for the velocity at 0.2. Point being, 0.2 is equal in both cases to the volume flux. Okay. Something to note actually in these types of equations is that for the continuity equation to work, or for the velocity to be changing according to the area, a force must be applied for that to happen. But that will be demonstrated in the later units where you include the momentum and the energy equations, because that will then describe the relationship between pressure, velocity, and density. But right now, we're just focusing on velocity, area, and volume flux. Okay. Question 2 is a pipe junction. So the only difference between this question and this question is that we have more than one exit point or input point. So one thing that's really important when you're dealing with a pipe junction is that you have to define your input and output section. So based on the arrows in this diagram, I've said that the input is at Q1. So I know that the input is 0.6 meters cubed per second, right? So can somebody tell me, I don't know if you guys saw, but can somebody tell me what 0.6 would be equal to, given that that's the input and then the output is up to you to write down? Like in terms of Q, what would the output be? So it would be Q3 plus Q2, given that you are defining, or I defined, Q1 as the input. Correct, yes. So that is the application of the continuity equation, which is down here. Okay, so what I wrote down here is kind of misleading, but the sign doesn't actually matter, right? That's the rate of the flow. It doesn't actually matter what sign it is, unless they're asking for a direction, which in this case they're not.
Sorry, can I say that?
Yeah.
Again, this is from the
Yeah.
previous workshop when we ran it last time. But do you remember in the 200 with reaction? Choosing a direction. You choose a direction, and you roll with it, you get a negative number, you just use it with the arrow. So sorry, just scroll. So
Yeah.
Q3 would be going the other way. Yeah, Q3 would actually be an input. Okay. Because you see how those numbers 0.6, 0.8, maths just doesn't be a negative, right? It'd be a negative.
Okay. So in this question, they were actually asking us to find the average velocity at point 3. So after we found Q3 there, once we find the relevant volume flux, we can always find the velocity as long as we have A, which we can find out through the diameter. As you can see, it's 0.5. And then very similar to the previous question, you just sub it into the Q is equal to A times U equation, and then that gives you the average velocity here. Okay. All right, I might just, oh, you know what, this question is kind of important. We'll do this one too. So this example is a river confluence, which is another type of continuity problem that you might be taught about in your course. So there's two parts to this question. Part 1 is finding the volume flux at point 1 given the other two volume fluxes, 50 and 54. And then the second part is to actually find the height of the river if it's a rectangle, or their control volume is a rectangle, which they've kind of drawn out for you here, right? So let's not worry about that for right now. Let's worry about part 1. Again, we're setting up our input and output equation. Here, they've said that Q1 and Q2 is equal to your input, which means Q3 must be equal to your output. So what they've done is that they've used the given values 54 and 50, and they've minused them to get Q1, which is 4 meters cubed per second. And then they've moved on to part B. So does everyone understand how we got to part A? Yes? Okay. So part B is finding the height of the river, given that now we have Q3, sorry. So they've told us that the river itself is a rectangle, and they've also drawn us the rectangle here. So we know from the question that the length of the rectangle is A. So all we have to find is the breadth or the height of the rectangle, which we can use by subbing in 54, which they've actually given us in the question. And by using the length and the I don't know what's going on here. Hold on. Oh, the flow velocity. They gave us the average velocity here, 0.9 meters per second, which we subbed in as u, and then this part here is just your a. So then you just solve that like a regular algebraic equation. Sorry, I kind of forgot I forgot what happened there. Did that make sense? Okay. Okay, this is a very similar example. I probably won't run through it right now, but again, you're just using the same continuity equation. You're breaking the A component up into the right area formula, that's actually quite an important thing to do. So you have to figure out what your cross-sectional area is. So like as the water is flowing through, you have to know what that area is so that you can like correctly sub in the right values into the Q is equal to A times U equation. And yeah, that's how they found H in this question. Okay, part 5 is the sedimentation tanks and residence time section. So sedimentation tanks is something that you'll learn a bit more about in wastewater, but it's kind of important to know what they're used for right now. Basically, they're just tanks and they kind of use the change in depth of like the water level to figure out how quickly the water is flowing out of the tank. So let's say it's like filled at a certain time. They'll use the change in depth over time, like at the end of the day, let's say they check it again, and then they'll use that length to determine how quickly the water flowed out of the tank, basically. So another term to remember is residence time. So that's the total time taken for the water parcel, which is basically the water that gets stuck in like the control volume. So it's the water that has entered the tank and is now like flowing out. And so the time taken for that water parcel to be exchanged is the residence time, or T-res as it's notated here. So in this example, this is the sedimentation tank. It's a bit difficult to see, but your length of the rectangular prism is 30 meters, the breadth is 10 meters, and the depth is 4 meters. One thing to note is that you've got your Q here, so you know that the cross-sectional area is this rectangle here, and you know that the Q is equal to 0.3 meters cubed per second. So the first step is to find the residence time. I've given you the formula here, so if you want to note anything down, I would probably write that one down. You're going to have to do a bit more maths here just to figure out the U, because they haven't given you the average velocity yet, so that's no worries. We just go back to the continuity or volume flux equation and rearrange it to make U the subject. They've given you Q. You can find out A using your breadth times depth, and that U eventually gives you 0.3 over 40. And then you know the length is 30. So that becomes 4,000 seconds, and you just convert it to hours to find your residence time. To find the vertical setting velocity, vertical setting velocity, which is the amount of, or how quickly it takes for the water level to go like from like this height to this height, you use a very similar formula. So they've just got L over U is equal to the depth over the vertical settling velocity. So it's the same equation, except you're just dealing in the vertical direction. So in this case, you'll notice like in the first part of the question, you use the length part, which is the 30 meters. Here you use the vertical change in distance, which is the depth. And then you put that over the vertical settling velocity, rearrange it, and then you get your vertical setting velocity here. Does that example make sense to you, everyone? Great. Okay. Right, I might leave this section for you to go through in your own time, but I'll just explain the concept behind these two questions very briefly. Sometimes when you've got like a storage container, it won't be as nice as like a cylinder or a rectangular prism where the cross-sectional area is fixed, right? Like in a tank, if there's water flowing out of the tank, the cross-sectional area is not changing, right? It's just the volume that's flowing out of the rectangle like constantly. But sometimes you have an area that's decreasing. So let's say, like, think of a funnel. Like the water is flowing out, right? But the area is changing over time. So at here, the diameter might be this long, but then here, the diameter might only be like a small circle, right? So in this case, you actually have to use integration to account for the change in area, which will affect the velocity and or basically how quickly the fluid flows out of the tank. What's happening here?
Sorry, I'm trying to assist with this.
Oh, that's okay.
Yeah, but it's,
Okay. But does everyone understand what I just said, like the concept behind that problem? So here, I won't go into too much detail, but see how you've got like a cone here in this part? So you can see the area changing as well as the depth. So we've just used integration to figure out the change in velocity over time. Okay. So before we move on to energy, something important to note is that continuity is only concerned with kinematics. So I kind of highlighted the syllables there to kind of help you remember. But why that's important is because going back to what we were discussing before, we're not actually concerned with pressure at all if we're working with kinematics. We're only concerned with like the movement of the fluid and how quickly it's moving through the exit point. When you include flow dynamics, that is when you will incorporate the stuff that Henry was talking about earlier, which is like the pressure at a certain point. And there is a way to relate all of those things together, which is the energy and momentum equation, right? Which I'm about to get into. This is not really too important, what is happening here. This is just an explanation of the fluid formations that you might deal with. So the difference between Eulerian and Lagrangian formulas, you don't really need to know all of this maths. You just basically need to know the difference between the two. So don't get too freaked out by what you see on the board right now. But Lagrangian is basically tracking an object or particle over time. So like given the starting position of a particle and the velocity, like how far will the particle be at this time, or what is the time when the particle is like at this point. And then the Eulerian formation is like a grid, and so that's basically asking like what is happening when you pick a specific point in space and time, like what is the velocity at that point basically. Okay, now we're moving on to energy. So this section here, so these notes are from when I did fluids. You don't need to pay too much attention to what's happening here if you understand everything that I just told you about continuity. But I just wanted to include it because this is your general energy equation here. So as you can see, it's the relationship between pressure, volume, velocity, and density and depth, right? So that equation is really important. They'll use it in a lot of your problems going forward. So it's very important to know, firstly, how to use it and how to rearrange it, because more often than not, your questions on Bernoulli's equation, which is like the derivation from the general energy equation, how they get you to use it is that they'll ask you to find like one component. So let's say they'll ask you to find the depth of a fluid or a river or like a tank, and you'll just have to rearrange Bernoulli's equation to find that component. And another important thing is that it won't always be so easy as like them giving you the density and the velocity and like using then gravity to find Z. They'll use terms like pressure head and piezometric head and elevation head. And so you'll just have to remember that the pressure head is equal to this section of Bernoulli's equation. So let's say I want you to find elevation head, right, which is Z. And then in the question, they've given you the pressure head, which is equal to like A, and the piezometric head, which is equal to B. They might not have given you any like symbolic values, but if you know that the pressure head is equal to this section of Bernoulli's equation and the piezometric head is equal to this part of Bernoulli's equation, then you'll be able to rearrange it, right? As long as they give you the constant here. Does that make sense? Okay, great. Assumptions made when using the Bernoulli's equations is that it's incompressible flow, frictionless flow, steady state flow. There's no change in temperature, so no heat transfer, and there's no energy added. So this is just the relationship between your pressure, your density, and your velocity. Okay. So Bernoulli's equation makes it even easier to solve continuity problems. So this example here, the final example, is another pipe extension, but it kind of incorporates both the continuity equation that we used in part 1 and also the new Bernoulli's equation. So here they've given you these values here, so both the diameters at point 1 and 2. They've given you the average velocity at point 1 and also the pressure at point 1. So the unknowns, they've given you 2 unknowns, which can anyone tell me what that means if they you get given 2 unknowns? Like, how do you solve the question? I kind of said it before. It's like very similar to high school maths. Yeah, you need two equations, right? So that's a really, I know it sounds silly, right? But it's actually a really important thing to remember, because I remember one time when I was doing my like fluids workshop, I just like couldn't figure out how to solve this question because I was only using one equation, and I was sitting there doing a lot of working out. But if I just remembered from the control volume part that I needed 2 equations, then I would have remembered how to solve it, right? So, okay, yeah, step 1. The easiest thing that you can do in any continuity problem is to just use the continuity equation and apply the continuity equation to your system here, right? So you know that at point 1, you've got a velocity of 0.5. You also know that the area is a circle with a diameter of 4 centimeters, so you can sub that in as well. And you know, most importantly, that is equal to the volume output, which you know the diameter, which means you know the area, and therefore you've got only one unknown there, which means you can solve for the average velocity at 0.2. So does everyone understand how we got 0.125? Okay, so now that we've got the average velocity, we can actually use Bernoulli's equation to find the pressure at 0.2. So, I mean, it's not too hard. You're just subbing in the values that you already know. Be very careful of your units when you're using Bernoulli's equation as well. They tend to be quite tricky with those. But as you can see here, the pressure that was given to us at 0.1 up here has been subbed into the pressure head. We know that the density is 1,000 and we know that the gravity is 9.8. So the pressure head has been solved. Same for the piezometric head, because we know that the average velocity at 0.1 is 0.5 and we know that gravity is 9.81. So the piezometric head is also solved. we rearrange it so that Z is, oh no, we don't care about Z actually, because the points that we're examining, notice how it's in a straight line. So the streamline that we're examining at point 1 and 2, there's no change in depth. So if there's no change in depth, it's 0, right? Or the difference in depth is 0. So we can cross those two out and then just solve for the pressure at point 2. Does that make sense? Okay. This part here, I think I forgot to go through this during the last fluids crash course. So I just wanted to show you quickly. This is kind of an overview of weeks 5 to 10. So weeks 5 to 7 will be a little bit more about pipe flow. 7 and 8 will be dimensional analysis, which is it's not, yeah, it's a bit different to the rest of the course. To be honest, I'm not really sure anymore why we need it, but that's what week 7 and 8 will be about. And then 8 to 10 will be a little bit more about the forces applied to a fluid in a pipe, and it will be like that concept will be used to kind of complicate the problems that we've gone through together. But that's all for the content. I do have a quiz. It's not too bad. I hope it's not too bad.
Hey, let's go. Absolutely shitting this.
Okay. Good job. That was actually really well done. Okay. So I'll just go through them really quickly. It shouldn't take too long. But the continuity flux types is mass, volume, and momentum. Energy wasn't part of the continuity flux types that we went through, but there is an energy equation that kind of involves the relationship between energy, pressure, density, and volume and velocity. Okay, so an example of a closed system in fluid mechanics is a water pipe. It just has to be closed to the atmosphere, so there can't be any like effects due to atmospheric pressure, for example, on the fluid. Okay, this is really good. I think last time we did this, everyone got this wrong, but basically this one's correct because if you consider this to be the input, it's equal to Q2 plus Q3. I think what everyone did last time was that they said it was equal to oh, thanks. Yeah. What everyone did last time was that they said it was equal to like Q2 plus Q3 plus Q5, which was like option, oh my goodness, option D, I think, was a popular one back then. But yeah, basically, if this Q1 is the input, then it's equal to all of the output points after that, which means it's equal to Q2 and it's equal to Q3. Q4 and Q5 would be equal to whatever Q3 is at that point. Okay, next question. Oh, we got this one right as well. Great. Okay, so residence time. Yeah. This one, I mean, it's just a definition, so it's just the time taken in the content called bucket hydraulics, which is what basically when you've got like a closed, well, not a closed tank, but you've got a storage section and you're like letting the water flow out of that storage section, and it's just the time taken for all of it for the whole thing to empty, right? And then, oh, I kind of gave it away, but bucket hydraulics is the term for a situation or a system where the water storage varies. So where you start with a certain volume and then over time that volume decreases or increases. Yeah, we got that one right. That's good. And that's it. That's all. Yeah. Okay. Great. Oh, how do we?
Maybe one more thing I want to quickly mention. If you remember back to 1300, you might have learned it in this form or another form, but this is for work energy. So your partial work energy equation. That's your kinetic energy. That's your work. That's your gravitational potential energy, and that's elastic, right? Elastic potential. So this is for your particle work equation, right? And Bernoulli's equation is basically this, but in different form. I forgot the exact equation. It's like a pressure one, right? Pressure head. So your kinetic head is just your kinetic energy component. Your elevation head is just your gravitational component. And then the pressure one, it's not really related because pressure is a fluid property, and the elastic thing is specific to when there's like a spring. So that's like for particles with like springs in the system. And the other thing to note with Bernoulli's equation, all these are in head, which is technically in meters, right? But it's basically just joules divided by gravity. Which is joules over meters squared, meters per second squared, right? And that just happens to equal meters. So that's what head is basically. That's one of the questions we got before. Alright, that's all. Yeah, you're free to go. You can fill out this feedback form if you want to. Stop the recording.